Hello students, welcome back to the sixth video of this playlist. In this video, we will be solving question number 6 from the most recent past paper of further pure mathematics, which is the May 2024 F1 paper. So let's get started with question number 6 of this paper. Okay, at first, part A. So here the question is asking to prove by induction that for n element positive integers 1 r 02 to the power whole n, that's the left hand side, equals 1 2 to the power n minus 1 bracket r 0 2 to the power n, that's the right hand side. So basically this is a 2 into 2 matrix, so where r is a constant. Okay, so we need to show that this left hand side, the matrix on the left hand side, it is equal to the matrix on the right hand side. So we have to prove by induction method. Okay, so the first step of proof by induction is that we have to prove that the given statement is true for n equals to 1. So that's what we will do. When n equals to 1, left hand side it is 1, left hand side equals to 1 r 0 2, that's the left hand side. Okay, now the right hand side, it is equals 1 2 to the power 1 minus 1 2 to the power 1 minus 1. Okay, so 2 to the power 1 is basically 2, so 2 minus 1 r, then 0 is there, and then 2 to the power 1. So 2 to the power 1 is basically 2. Okay, so if you multiply out the bracket, then you will get just 1 r 0 2. Okay, so that's the right hand side. So we can see that for n equals to 1, left hand side is equals to the right hand side. So we can say that hence the statement is true. Statement is true for n equals to 1. Okay, the second step is we have to consider that we have to show that the given statement is true for n equals to k and n equals to k plus 1. Okay, so this is called the inductive step. So in inductive step, we will not directly show that for n equals to k the given statement is true, or we will not directly show that the given statement is true for n equals to k plus 1. We have to do some induction here. Okay, look, so in the second step we will consider when n equals to k, if n equals to k, then the left hand side it is basically 1 r 0 2, the power is k. Okay, this is the left hand side, 0 2. Okay, that's the left hand side. This is equals, the right hand side is 1 2 to the power k minus 1 times r. Okay, 1 2 to the power k minus 1 times r, and then 0, and then this is 2. Is it just 2? Yeah, it is 2 to the power n. So in this case it will be 2 to the power k. So this is the equation when n equals to k. Okay, now when n equals to k plus 1, we will have the statement on the left hand side, it will be 1 r 0 2 whole to the power k plus 1. The power is n on the left hand side, so in place of n we will have k plus 1. Okay, now the thing is, in induction step, what we need to do, we need to represent the statement of the left hand side in terms of n equals to k. Okay, we have to represent the statement for n equals to k plus 1 in terms of the statement n equals to k. Okay, so how can we do that? Have a look. 1 r 0 2 to the power k plus 1, it can be written as 1 r 0 2 to the power k times 1 r 0 2. Okay, now you just need to substitute What we need to substitute? We know that 1 𝗓02 whole to the power k. This is basically 1 2 to the power k minus 1 times 𝗓02 to the power k. Okay, we will just substitute this expression in place of 1 𝗓02 whole to the power k. Okay, so let's do that. So you will get, this is 1 and this is 2 to the power k minus 1 r, and then this is 0 and this is 2 to the power k. Okay, and times 1 r, if I'm not wrong, let me check it out. 1 2 to the power k minus 1 r 0 2 to the power k, and this is 1 𝗓02. Okay, 1 𝗓02. Okay, now just multiply. Let's multiply. Okay, if you do multiplication, this is 2 into 2 matrix, so 1 times 1 times 1, it is basically 1, and then 2 to the power k minus 1 times r times 0, this is basically 0, so nothing else, nothing with 1 is only. Okay, then 1 times 1, okay, 2 to the power k minus 1 times r times 0. Okay, next is 1 times r, that would give you r. 1 times r, this is r. 2 to the power k minus 1 times r times 2, that is plus 2r times 2 to the power k minus 1. That's it. So this is just matrix multiplication of 2 into 2 matrix. Then go to the lower row, 0 to 1. 0 times 1, it is 0, and 2 times 2 to the power k times 0, it is 0, so this is 0, and then 0 times r, it is basically 0, and 2 to the power k times 2, that would give you 2 into 2 to the power k. Okay, now you have to simplify this expression. Okay, so if you do simplify it, what you will get? You got r there, you got 2r, so we can take r common from here. So if you take r common from here, you will get 1 plus 2 times 2 to the power k. So 2 times 2 to the power k, 2 times 2 to the power k minus 2 times minus 1 times 2, which is negative 2. Okay, we have taken r common, and then 2 times 2 to the power k, it can be written as 2 to the power k plus 1, and it remains as 0. Okay, now if you further simplify it, you will get 2 to the power k plus 1. Okay, so 2 to the power k plus 1 minus 2 plus 1, it is basically minus 1, right? So r was common, so r will remain as it is, and then we got 2 to the power k plus 1 and 0, it remains as it is. Now what you can see? We can see that if we had substituted k plus 1 on the right hand side, okay, if we had substituted n equals to k plus 1 on the right hand side, then exactly we would get the equation that we have derived just now. Okay, so this equation, this expression, this matrix expression has been derived using the expression of n equals to k. We didn't substituted n equals to k plus 1 directly on the right hand side of the statement, right? We have used the expression for n equals to k to approach this expression, and for expression for n equals to k plus 1. That means that means we have showed by induction method that we have approached the right hand side of the statement using the statement of n equals to k. So this proves that the statement is true for n equals to k, and since the given statement is true for n equals to k, then the given statement must be true for n equals to k plus 1. That's what we have to make a statement at the end of the answer. Here it has been proved that the given statement is true for n equals to 1, and if it is true for n equals to k, then it is true for n equals to k plus 1. Then it is true for n equals to k plus 1. So we have showed it is true for n equals to 1, it is true for n equals to k, and it is also true for n equals to k plus 1. Hence proven the given statement is true for n element all positive integers. That's what the question in part A of question number 6 has asked to prove. Fine. Okay, next is part B. In part B, the question says, okay, they have given two matrix M, which is 4 0 0 5, and matrix N, it is 1 minus 2 0 2 whole to the power 4. The transformation represented by matrix M followed by the transformation represented by matrix N is represented by the matrix B. Okay, so part B1 is asking here to determine the matrix N in the form A, B, C, D, where A, B, C, and D are integers. Okay, so the matrix N, it is given as 1, -2, 0, 2 whole to the power 4. So basically, we will use the concept from the part A, from the statement given in part A to approach this answer. So in part A, we have showed that when 1 r 0 2 whole to the power n is a matrix, then we can write it as 1 2 to the power n minus 1 times r 0 2 to the power n, right? So that's how we can represent the matrix n. So for part B1, matrix n can be represented as, where's the statement, the value for n, the power of the matrix n, it is 4. So that would give you 1 and then 2 to the power n minus 1, right? 2 to the power n. So 2 to the power n, that is 2 to the power 4. The power of n here, it is basically 4. So 2 to the power 4 is 16. So 16, okay, let me write it down at first. So 2 to the power 4 minus 1 times r. The value for r, it is basically -2, and this is 0, and this is, okay, is it -2? Yes, the value for r here, it is basically -2. Okay, and this is 0 and then 2. So in this place, it will be 2 to the power n. So that would be 2 to the power 4. It would be 2 to the power 4. Now calculate the numbers within the matrix. So 1 0, 2 to the power 4 is 16, 16 minus 1, it is 15, so 15 times -2, it is -30, and 2 to the power 4 is basically 16. So matrix n is basically 1 -3 0 16. So here A is 1, B is -30, C is 0, and D is equals to 16. Isn't that the format the question has said? A, B, C, D. Okay, A, B, C, D. Okay, A, B, C, D. Exactly, that's the format the question has asked for. Okay, and that's the answer for part B1. Fine. Okay, next is part B2. In part B2, the question is asking to determine the matrix B. So already they have mentioned the matrix B is basically the transformation that the matrix B represents. It is the transformation of matrix M followed by the transformation of matrix N. So that means the matrix B can be written as B equals to, which one comes first? The one which is said after followed, okay, followed by the followed by the transformation represented by matrix N. So N will come first because it is followed by. So followed by N, then M comes. So matrix B is N M. Okay, for part B2, for part B2, for part B2, matrix B, it is N M. So N is given by, okay, matrix N, it is given as we found in part B1, which is 1, -30, 0, 16. 1, -30, 0, 16. And matrix M is given in the question. Matrix M, it is 4005. Okay, 4005. 4005. Okay, now do the multiplication, matrix multiplication. So 1 times 4, it is basically 4. -30 times 0, it is 0. Basically row to column, right? 1 times 4, -30 times 0. That's how we multiply. So 1 times 0, -30 times 5, it is -150. And then 0 times 0, okay, 0 times 4, it is 0. And 16 times 0, it is basically 0. So this is basically 0. Just matrix multiplication. And then 0 times 0, it is basically 0. 16 times 5, it is 80. That's it. This is basically the transformation matrix B. Fine. That's what part B2 has asked to determine. Fine. Okay. Next is part C. Here the question says hexagon S is transformed onto hexagon S prime by matrix B. Okay, so the hexagon S, it is transformed to hexagon S prime by transformation matrix B. Given that the area of S prime, the area of the hexagon after being transformed, it is 720 square units. Determine the area of S. Okay, we have to find out the area of the original hexagon. Okay, so we know that as we transform a matrix, as we transform a shape using a transformation matrix, then the area is changed by the scale factor of the determinant. Okay, so we have to find out the determinant of the matrix B at first in this case. Okay, so for part C, determinant of matrix B, determinant of B, it is AD minus BC. So this is, if I say matrix B, this is 4, -150, this is 0, this is 80. So this is A, this is B, this is C, this is D. So AD minus BC. So A times D, it is 4 times 80 minus BC. So B is 0. So 0 times -150, it is basically 0. So determinant of B, we got here, it is 320. Okay, so the scale factor, as we transform the shape, the hexagon, by the matrix B, the area of S multiplied by 320, it will get multiplied by 320, and then we will get the area of S prime. Okay, so the area of S prime, it's given as 720, right? So we can write the area of S. We need the area of S. So area of S, it is equals to 720 over 320. So 320, is it, what's the unit? Is it unit squared or square units? Okay, so this is basically that much unit squared. Okay, so the area of S, you will get 720 over 320. That would give you 2.25 unit squared. That's the area of the hexagon S. And that's the answer for part C from question number 6. Fine.